Yay. So good evening, everyone. I'm Shivani Thok, and I welcome you all for this course of digital signal processing and its applications. And I welcome you all for the week 1 tutorial of this course. So I'll be taking tutorial for this course every week from 6 to 8 p.m. And the nature of this tutorial will be like first 15 to 20 minutes. I'll take up the recap of whatever has been covered in the particular week and followed by some assignment questions. So these questions will be little bit closer to whatever you get in your assignments. However, they won't be the same questions. Along with that, generally we take up last year's assignment questions as the questions that the TAs will be solving this time. But in case the previous year's questions are same, then some other additional questions will be taken up. You are free to unmute yourself at any point of time and ask me the doubts. Another thing is unmute yourself, as I won't be able to see your chat box. So unmuting and asking questions will be a better thing to do. You can also raise your hand in order to ask questions. I will request you to unmute in that case. So let me just quickly start with the first tutorial with the recap of week 1 content. So this week 1 was basically a very introductory week. It started with why we need this particular kind of course and why we need to understand the contents of this course in a better fashion. So this started with a very basic idea about what a signal is, what are independent and dependent variables, what are continuous time or continuum, or what is continuous dependent variable, continuous independent variable. So let's quickly start with that. So before going into continuum, let me just quickly give you an idea about what a signal is. So a signal is basically a mathematical function where it has a dependent variable, which we generally give it in the y-axis. So it is generally a dependent variable. And this dependent variable varies with as the values of your independent variable changes. For example, if I have my voice, then the fluctuation in my voice level or volume is my dependent variable, which is changing with respect to the independent variable of time. So this can vary based on different scenarios. For example, images is change of light intensity across the space. Video is change of light intensity across the space as well as across the time, and so on. Now, these variables, that is, this dependent and independent variables, can be of two types. One is continuous and another is discrete. Yeah. Okay, I'll request everyone to unmute yourself till the time you want to ask a question. Otherwise, it will unnecessarily create a disturbance. If you want to ask a question, just unmute yourself. Otherwise, please be on mute. Okay, so we have dependent and independent variables. So this dependent and independent variables can be of different can be of two types. One is continuous and one is discrete. So what do we mean by continuous variables? So by continuum, what we mean is if I look at two values for this particular variable, let's say between 0 and 1. In between these two values, I can find another value. Let's say this is 0.4, which is closer to this 0 as well as this 1. Similarly, I can find another value, let's say 0.2, which is between the 0.4 and 0 and 0.4, which is again closer to 0 and 0.4 than 0 being closer to 0.4. So whatever small value, small point we want to figure out between these two, we will be able to find out a number between those two values which is closer to both of them. So this is basically continuum. So all the naturally occurring signals are having continuous dependent variable and continuous independent variable. When I'm speaking, there is no notion of discretization of time and my amplitude. So naturally, my voice is having a continuous nature in amplitude as well as a continuous nature along the time axis. However, when we go for discrete things, so what happens is I will just look at 2 points. Now let's say 3 points. It says 0, some t and 2t. Now there won't be any value present in between them. So if we have anything here, the closest thing will be this time. So there won't be any value to be considered here. So this we can also index by 0, 1, and 2, and so on. So this is the nth discrete sample, or let's say first discrete sample, second discrete sample. Now if I look at 0.5, no, it is not there because we are discretizing it at a level of or a granule of t. So this 0.5 won't be present in this particular set of discrete time, discrete variables. Now, in this particular course, what we will be doing is we will be looking at the signals which are continuous along this dependent variable. However, they will be discrete along this independent variable. Why is it so? Because we want to perform some sort of processing using our computers. Now, our computers can't handle continuous time signals because at every given time instant, whatever time instant you say, you will get a particular value. So, you will need a huge memory to store this large signal. So, therefore, in order to understand or to process these signals in a better fashion, what we will do is we will consider discretizing this independent axis. And discretizing this independent axis means picking up values of dependent variable at fixed durations like this. For example, we'll take up the value at this instant, at this instant, at this instant, and so on. So let's say at t, then at 2t, 3t, and so on. And we will just pick up these particular values. This process of going from a continuous independent variable to a discrete independent variable is known as sampling. So what does sampling do? It allows us to move from continuous independent variable to discrete independent variable. Okay. So this process is known as sampling. And here we have picked up values at time instance t, 2t, and so on. Like we are taking up values after every tth time instant. So therefore, this t is known as the sampling duration. So what we are doing, let's say we have a signal x of t. This is having continuous independent variable. So here this anything inside this bracket is our independent variable and anything outside this bracket is our dependent variable. So this is continuous. So what we will do is we will sample it at n or at time instance t equal to nt, where this t is, so this capital T is known as the sampling duration. And what it will give us? It will give us x square bracket n, which will be the values of x which are obtained at time t equal to n t. Another thing that we need to keep in mind here is, let's say fs is equal to 1 by t. This is known as, this particular frequency is known as sampling frequency. And what does sampling frequency tells us? So this sampling frequency tells us that how many samples we get in 1 second. Okay, so this is all about the sampling. Then we moved on to a special case of signals, which is sinusoids. We looked at sinusoids because they are smooth signals and they have all the possible order derivatives well defined. Such kind of signals are known as analytic signals. We won't go into too much detail about analytic signals and those things. That is not the scope of this course. But yeah, this is a good point to keep in mind. If we have all the infinite, all the order of derivatives well defined, those kind of signals are known as analytic signals. So first we looked at these sinusoids. Let's say that sinusoid is given by x of t equal to a naught cos of omega naught t plus phi naught. So here, this a naught is its amplitude. This omega naught is its angular frequency. So this angular frequency, omega naught, is basically 2 pi f naught, where f naught is basically its Hertz frequency. And this phi here is the phase. Okay, so this is the standard definition of our sinusoid. And first we looked at sampling of sinusoids. So what we saw was, when we are sampling it, let's say with a frequency of sampling frequency of fs. So let's say this is 0. This is the original sinusoid, which is located, which is available here. So when we sample it, let's say at sampling frequency fs, then we will have replicas of these signals which are located at fs plus f naught, fs minus f naught, then at every integer multiple of our fs, 2fs plus f naught, 2fs minus f naught. So in that case, what we will have is, here our amplitude was a naught and phase was pi naught. For these replicas, what we will get is, here we'll have amplitude as a naught and phase as phi naught. However, for the mirror image that we are having here, we will get amplitude again as a naught, but my phase will be flipped. It will be minus phi naught. And this kind of thing will be available at every integer multiple of our sampling frequency. Okay, so these replicas are going to be present every time. Now the question that we wanted is, we wanted to sample it in such a way that we can recover back this original sinusoid. So this original sinusoid only has the frequency components which are located in this particular region. So if I am able to just retain this part using some low pass filter, if I'm able to do that, then in that situation, I will be able to retain back my original signal very nicely. Now, when can I have this retaining possible? When this particular frequency, that is this fs minus f naught, is greater than this f naught. So from that, what we got is, so for reconstruction of the sinusoid we will use a low pass filter. We will look at what filters are in the coming lectures. Just assume that it is some system that just allows us to retain this particular frequency component and ignore everything else. With cutoff frequency, what is this cutoff frequency? This particular frequency that is available here, that this FC. So this frequency FC, which is less than your Fs minus F naught, but greater than F naught. So from these two things, what we get is my Fs should be greater than 2 times F naught. So if this is true, we can have, or we will get proper reconstruction. Or we will get x of t from x of n. Now suppose we have opposite thing. So if Fs is less than 2 times F naught, what will happen? This is 0. Let's say this we had F naught. Then we had, let's say, Fs here. Then due to the presence of replicas, we'll get something like Fs minus F naught here. And then we will have Fs plus F naught. And again, this will go on happening. Now, if I want to recover back this particular thing, and I try to use a low pass filter with cutoff frequency, let's say FC, something like this. Now, this particular thing or this particular frequency component was not present in original signal. This component was absent in original signal. And this kind of thing, whatever is happening, is known as aliasing. So this was not present, but it is now coming up as a false thing. And such kind of things are known as aliasing. So for any particular signal, which is having a maximum frequency, or which is having a frequency domain representation as something like this, that is, it is having some maximum frequency, it is 0 afterwards. In that situation, the sampling frequency should be greater than 2 times this maximum frequency. This particular relation is known as the Nyquist sampling theorem. And this is the condition which we use to design or to choose the sampling frequency for our particular system, for our particular signal. After we looked at this sampling of sinusoids and aliasing, we said we'll then look at the discrete systems. So what do we mean by a discrete system? So a discrete system is something that is taking in a discrete time input or a discrete input and leads to a discrete output. And we want to develop a relation between these two. We want the input output relation between them or between, let's say, xn and yn, which is similar to what happens in this x of t and y of t. So basically, this x of t sample version is y of t, and this x of t sample version is x of n, and y. Wait a minute. X of n is the sample version of this x of t, and y of n is the sample version of this y of t. So we want to develop this particular input-output relation, and we'll dig up more in these things when we proceed in this particular course. So this is all about the uh, recap of this particular week. If you have any queries, then please let me know. Otherwise, I'll move on to the questions that I have planned to cover today. Okay. Okay, so let me start with the questions that I have planned to cover today. Okay, so the first question is, how many samples are required so that we can perfectly reconstruct the signal given by y of t equal to a e power bt? Assume that it is known that the signal function is an exponential function. So what is given to us is that this y of t is equal to a into e power bt, and it is given to us that this function is exponential function. We know that. So what does that mean? We know that the function takes this particular form. And what we need to do is we want to know how many samples are required to perfectly reconstruct this particular signal. Now, since we know that this function takes the value, takes this particular form, it is enough to know what is the value of this a and b. If I know the value of this a and b, I will be able to substitute the value of t and then come up with the value of yt for any particular given t. So what I'm trying to say is, since we know that the function takes this particular form, it is sufficient to know the values of A and B so that we can get y of t equal to A into e power bt for all values of t. Okay, so now there are only two unknowns, that is this A and this B. So now in order to find out two unknowns, how many samples are sufficient? Two unknowns and two equations are more than sufficient to obtain this entire equation, or to or to reconstruct perfectly this entire signal y of t for all the values of t. Okay, so what it means is, if I know a and b, we can construct y of t for any value of t. So this A and B are two unknowns, which means two equations are sufficient to obtain the values of A and B. Okay. So now let's say that we have the samples at time equal to T1 and T2. Suppose we have the samples of y of t at t equal to T1 and t equal to T2. So what we have, y of T1 equal to a into e power b T1 and y T2 equal to a into e power b T2. So now what we can do is we can take ratio of these two. So we'll have y of T1 divided by y of T2 equal to e power b T1 upon e power b T2, which is equal to e power b T1 minus T2. Now if I take natural log on both the sides, what will I get? I will get natural log of y of T1 upon y of T2, which is equal to natural log of e power b T1 minus T2, which is equal to b into T1 minus T2. So therefore, this b comes out to be equal to 1 over T1 minus T2 into natural log of y of T1 upon y of T2. Now we can use this particular value of b and substitute it in any of these two equations to get the value of a. So let's say we substitute it in this first equation. So now what we can do is, therefore, y of T1 equal to a into e power b into T1. So here the value of b is 1 upon T1 minus T2, natural log of y of T1 upon y of T2 into T1. So therefore this a comes out to be equal to y of T1 whole divided by e power T1 upon T1 minus T2 into natural log of y of T1 upon y of T2. So this is whole in exponents. Okay. Yeah. So what is the answer to the basic question that was asked to us is how many samples are required so that we can perfectly reconstruct this particular signal when we know that it is of the form of an exponential signal. So for this particular question, the answer is two samples are sufficient. Okay. Now, next thing is, will our answer remain same if we did not know that yt is okay? Will our answer remain the same if you did not know that yt is an exponential function? So we don't know that this particular function takes this particular form. So for this particular situation, we will need we will need the knowledge about the frequency content and all those things. So if we do not know the nature of y of t is exponential, we need to know its maximum frequency. And in this particular situation, if you find its Fourier transform, here this has maximum frequency as infinity, which means we will need infinite samples to reconstruct y of t. Is it clear? Any questions here?
Hello.
Yeah,
So since we are having two unknowns, A and B, are you saying that two samples are sufficient?
correct.
Then in that case, not necessary to find the A and B values. Just by seeing the equation itself, we can say is.
Sorry?
In that case, not necessary to find the values of A and B. Just by seeing the equation itself, we can say. Yes?
No, no. We want to find or we want to reconstruct this y of t. We want. Okay, I didn't understand your question. Can you please repeat it?
You found the values of A and B. Yes?
Correct. Yes.
So what is the need for finding the values of A and B here?
Okay.
You are saying that
So we
by
just
finding
know that the function takes exponential form. We don't know what this a and b is. We just know that there is some constant getting multiplied to it, and it is of the form of e power some constant into time. We don't know the value of those constants. So now if I need to get the value of the signal for all possible values of t, I need to know precisely what my a and b are. Does this answer your question, ma'am? We just know that
sorry, I
it is of this exponential form. We don't know
yes,
a
it is
and
an
b.
exponential form. Okay, after finding A and B values,
Hmm.
what is the conclusion out of it? After finding the
So,
equations of A and B, what is the conclusion?
I just showed how to find the values of A and B. The basic question was how many samples you need. So to find A and B, we'll substitute those value in this equation and can get the values of this y of t for all the time instants. So
Yes, A and
in
B. So
order to
just by seeing
obtain
the
this A and
equation itself, yes.
sorry,
Okay. So you found the values of A and B, that is okay, madam. But
uh,
just by seeing the equation itself, if we know the
hmm,
values of A and B, we can find the
hmm,
values of y of t at any time period of t. Yes, simply
exactly.
we can say.
Yes.
Simply we can say. So I thought of asking that what is the need for finding the values of A and B only? That is what I my question.
If you don't know the value of A and B, then okay, I just found it for the sake of showing how to find it, and two values are sufficient. But if we don't know
Okay,
A
if
and
you
B, we
want to
don't know
find out the
anything
value,
about the
okay,
y of t.
okay. Yeah, if you want to find out the values of the sample, then we need the values of A and B. Then
Exactly.
to say, yeah. So, um, so here the A and B are the two constant values. So with that, how
Correct.
can you say two samples are sufficient?
How many? So this A and B are constant values, right?
Yes, two constant values to find the values of y of t. Then
Huh.
how you are saying that two samples are sufficient?
So if I know the values of A and B, even before observing this y of t for all the time instants,
Yes,
can't
yes,
I
A and B are the
substitute value of
A,
t? Have you
yes,
complete your
madam. A
question?
and B are the two equations. A and B are the two constant values you found out by means of some equations. That is okay.
Hmm. Huh.
After substituting with A and B, you are getting some y of t. Y of t in
Correct.
terms of A and B, we are having some values. Okay.
Hmm.
Then with that, we can substitute any values of t to find number of samples.
Hmm.
Then with the only with the constants A and B, how can you say two samples are sufficient for
Okay.
not getting the
Okay.
algebraic method?
Okay. So here, do you agree that if I know the value of A and B, I know the value of y of t for any time instance?
Yes, yes, that I agree.
Huh. Now wait. Now wait.
My
Now,
question is only with the constants we cannot say two samples are sufficient.
then how many are sufficient?
Yeah, that is what I
I
am
mean, I'm not
expecting your
able to
answer.
understanding the thought process actually. So what I'm trying to say here is, if you know A and B, we can substitute the value of t equal to 0, 1, 2, and so on for obtaining this y of t for any time instance. Now to
Okay, for
obtain
okay,
now to get the value of A and B, these are two constants, two unknowns. So for obtaining two unknowns, I need two equations. Am I right? So for obtaining those two equations, I will have to observe this y of t at two different time instants. So if I look at only two samples of y of t, or if I observe only two samples of y of t and get the value of A and B, I don't need to observe this y of t for remaining time instants. So now for any given time instant, I can tell you the value of y of t because I know A and B. Does this answer your question now? Hello.
it's okay, madam. Continue. It's okay. Continue, madam.
Okay, any other question? Okay, if there are no questions, then I'll
Only
move on to the second.
ma'am, only one sample is enough, right? If your complete equation is dependent on the constants A and B,
Hmm.
then if we just substitute T, T1, how many ever values, you can easily
Hmm.
derive how many samples with that, no? Because AT is a multiplication factor there, A and B.
Huh. So how will you find A in that case? So
Okay, so you're telling that for finding out A and B, how many samples you need.
correct, exactly.
Okay, if that is the case, then two samples.
Yes. So now if this
Yeah,
multiplicative
okay.
factor was not there, then what you are saying is correct. I just need only one
Yeah.
sample. But I
Yeah.
need to know
So
this
instead
A.
of the entire sequence, you're telling how are you going to find out those multiplication factors, A, B.
Yes.
Okay. Okay, ma'am.
Yeah. So this kind
Yeah.
of question was there in last to last year's assignment, in which something
Uh,
similar was asked. So
okay.
assuming the
Okay.
maximum frequency, people wrote the sampling frequency as the answer. However, since the nature of the signal was known, we just had to figure out how many unknowns are there and just figure out how to find those unknowns. So the number of equations that you need to find out those constant unknowns like A and B here was the answer.
Yes.
So this is
Okay.
something similar what was there in the last year's assignment.
Okay, okay, thank you.
Yeah.
Ma'am, and will we get access to the written notes that you're sharing here?
Yes, 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 yes. So this written notes and the recording of this videos will be made available to you. So this notes will be made available to you in an Excel sheet which NPTEL people will upload. And in that there will be a YouTube video link in which I will upload this video today itself. In
Okay,
case
okay,
it
thank you
gets
very much.
delayed to upload this particular thing from the NPTEL site, you can simply go to my YouTube channel and see the videos there.
Okay, okay, thank you.
Yeah, it will be made available. Don't worry.
Thank you.
Yeah. So let me move on to the second question then. So following discrete time system effectively acts as. So this is the discrete time system given to us. This is like a block diagram of the system that is given to us. So what is happening is this is my input. This x of t is my input. And sorry, x of n is my input and this y of n is the output. And what does this unit delay block does? So input to this here, if you observe this x of n is input to this unit delay block also. So whatever input is available to this unit delay block, it delays it by 1 unit. So output of this unit delay block is a delayed version of the input delayed by 1 unit. So now what is happening here is input at this end is again x of n. This particular thing here, this particular notation here is known as adder. And the sign here means you just need to add plus x of n. And the sign here means you just need to add minus of whatever input is available to this particular branch of this adder. Okay, so now using that, this output y of n is equal to this x of n minus this x of n minus 1. Okay, so what is this doing? This is basically taking current input and subtracting from it input in the previous time instant. So what it is doing is it is basically finding the difference between the current input and the immediate past input. So it is finding the difference. So such kind of system for for a discrete time system is known as the differentiator. So this such kind of system is known as the differentiator system. So this whatever questions I am taking up now in this particular session are from the last to last year's assignment, because there are some overlaps in the questions in this year's and last year's assignment. So this is a fact that is being told in this particular question. It was asked in last to last year's assignment. So yeah. So basically it is an equivalent of differentiator in time domain, first order differentiate to the first order. So it is just subtracting the previous time instant from the previous time instance input from the current time instant. Any questions?
Good evening, ma'am. Can we say
Yeah.
that the yn is as a impulse signal? Xn minus x.
Yes. No, 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 no,
Is
no,
a
no. No, no, no. If your xn is unit step function, then whatever you're saying is correct.
okay.
We'll come to that in next week. This is any generic input, sir.
Okay. Okay.
Yeah, we'll come to that impulse and all those things in coming week. For now, let's just be very simple and not go into whatever has not been introduced. But yeah, whatever you're saying is along the correct direction. However, this x of n should be a unit step. We'll see that. We'll see that in next week. Any other question? Okay, if there are no questions, then let me move on to the third question. Okay, the analog signal x of t is given by xt equal to 2 cos. So this signal is x of t is equal to 2 cos 2000 pi t plus 3 sine 6000 pi t plus 8 cos 1200 pi t. So what is said is this is the analog signal. What do we mean by analog signal? It is continuous in amplitude and continuous in time. So what do we mean by analog signal? So signal is analog when it is continuous in time, that is the independent variable, and amplitude, that is the dependent variable. Okay. So this is the analog signal or the continuous time signal that is given to us. And it is said that it is sampled at 5000 hertz. So this particular signal is sampled at 5000 hertz, which means its sampling frequency is, let's say fs is 5000 hertz. So what is asked to us is what is the discrete signal obtained after sampling? So how does that signal look? So the discrete signal which is equal to, let's say, x of square bracket n. And how do we obtain that? So the sampling process simply means that we are picking up values at every nth sampling duration. So here this t. So this was our signal which is given to us. This is the sampling frequency and this is the discrete signal, and we need to figure out how this particular signal looks like. So now here this t is the sampling duration. And this has an inverse relation with the sampling frequency, which is equal to 1 by s. So therefore, this t comes out to be equal to 1 by 5000. So now if I substituted this particular t here, so x of n comes out to be equal to x of n by 5000. Okay. Now what was our x of t? This x of t is given in this particular equation here. So let me just copy paste it the next page for our reference. Okay. So therefore, this becomes 2 times cos of 2000 pi, and my t is now n by 5000 plus 3 times sine of 6000 pi n by 5000 plus 8 times cos of 1200 pi n by 5000. Okay. So now if we simplify this, so therefore this x of n is equal to 2 times cos of 2 pi n by 5 plus 3 times sine of 6 pi n by 5 plus 8 times cos of 12 pi n by 50. Okay, so this is the discrete time signal which we have obtained by using the sampling frequency of 5000 hertz. Now the question that I am now asking is this sampling frequency good enough? I mean, is it satisfying our condition that this should be greater than or equal to our, it should be greater than the 2 times the maximum frequency available in this signal. So now let us try to understand if that is happening or not. So this is an additional part. Let's try to understand what basically is happening. So our x of t was 2 times cos of 2000 pi t plus 3 times sine of 6000 pi t plus 8 times cos of 1200 pi t. Okay, so now here, if we look at this, this is basically 2 pi f1t, which means that the frequency of this particular sinusoid comes out to be equal to f1 equal to 1000. Similarly, for this particular thing, it is 2 pi f2t, which means that my f2 comes out to be equal to 3000. And similarly here, again it is 2 pi f3t, which means that my f3 here comes out to be equal to 600. So what we are having is, we have, this signal has 3 frequencies. One is 1000 hertz, f2 is 3000 hertz, and f3 is 600 hertz. Okay. Okay. So now what we are having here is maximum frequency. Let's say f max in this particular signal is max of my f1, f2, and f3. So if my f1 is
F3 is 6000.
now 1200 divided by 2. It is 8 cos 1200 pi t. So 1200 divided by 2 is 600. Okay. So the maximum frequency that we are having here is 3000 hertz. So the sampling frequency should be greater than 2 times f max, which is equal to 2 times 3000, which comes out to be equal to 6000 hertz. But at what frequency we are sampling? We sampled it at 5000 hertz, which means we are not sampling it at an appropriate sampling duration or at an appropriate sampling frequency. So therefore, we will be having aliasing. So therefore, 5000 hertz sampling frequency is inappropriate. Any questions? Okay, if there are no questions, then let me move on to the next question then. Okay, so here what we are given is, given the following relations between the signal and the CTFT. What do we mean by CTFT? CTFT is the continuous time Fourier transform. Find the value of V of j omega, which is the continuous time Fourier transform of the signal V of t, where this V of t is given by the equation here, where my x1 of t has a Fourier or xi of t has Fourier transform as xi of j omega, and x3 of t is related to our x1 of t and x2 of t by this particular relation given to us. So now before solving this particular thing, let us quickly recap what this continuous time Fourier transform is. And some properties also will look. So here we have continuous time Fourier transform So this gives us frequency domain representation of a continuous time signal. What do I mean by continuous time? It means that the independent variables are continuous in nature. So suppose x of t is a continuous time signal. So this x of t is a continuous time signal. Its Fourier transform is given by x of j omega. And these two have one-to-one correspondence. These are unique pairs. Xt and x of j omega are unique pairs. So this x of j omega is given by integral minus infinity to infinity x of t into e power minus j omega t dt. And this x of t can be reconstructed using 1 over 2 pi integral minus infinity to infinity x of j omega into e power j omega t dt. Okay. So these are the synthesis and the analysis equations for this continuous time Fourier transform. Now there are various properties of this continuous transforms. In the interest of time, I'm not proving it. These proofs are there in the previous course of signals and systems, but I am putting it down so that it will be easy for us to use them. Okay. So the first property is the linearity property. So it says that if x1 of t has a Fourier transform of x1 of j omega and x2 of t has a Fourier transform of x2 of j omega, then a times x1 of t plus b times x2 of t, that is this linear combination, has the Fourier transform of a times x1 of j omega and b times x2 of j omega. This is the linearity property. The next one is time shift. So it says that suppose x of t has Fourier transform of x of j, x of j omega, then x of t minus t naught has a Fourier transform of x of minus x of j omega multiplied by e power minus j omega t naught. So it gets scaled by, or an additional phase gets added to it. Okay. And the last, another property that we will be looking at is complex conjugate. Property. So if x of t has a Fourier transform as x of j omega, then x conjugate of t has a Fourier transform of x conjugate of minus j. Okay. So this is there. Another thing that we will look at is time convolution property. So if x1 of t has Fourier transform as x1 of j omega, x2 of t has Fourier transform of x2 of j omega, then x1 of t convolved with x2 of t will have Fourier transform as x1 of j omega into x2 of j omega. Okay, is it clear? Any questions till this point? These are some properties of continuous time Fourier transform which we will be using. So this is just a short recap of continuous time Fourier transform. Since the next question is related to this, so I thought that let's take up these things first. So what is given to us is this v of t is x1 of t convolved with x2 of t convolved with x3 of t. So this is the relation between the v of t and x1, x2, and x3 of t that is given to us. Another thing that is given to us is the Fourier transform of this x1 of t, x2 of 3, and x3 of t, which are given by x1 of capital X1 of j omega, capital X2 of j omega, and capital X3 of j omega. So these we know. And another thing given to us is this x3 is equal to x1 conjugate of t minus t naught plus x2 conjugate of t minus t naught. So this is also known to us. This is also given to us. And what is asked is, what is the Fourier transform of this v of t? So if I take Fourier transform of this v of t, it is given by v of j omega, which comes out to be equal to x of j omega. So here we are having convolution in time. So that will translate to multiplication in frequency domain. So this will be x1 of j omega multiplied by x2 of j omega multiplied by x3 of j omega. So this is coming from time convolution property. Now we know what this x1 of j omega and x2 of j omega are. However, we are given this x3 of t in terms of x1 of t and x2 of t. So now let us figure out the Fourier transform this x3 of j omega. Okay. So what is given to us is x3 of t is equal to x1 conjugate of t minus t naught plus x2 conjugate of t minus t naught. Okay. So for that, let us first figure out the Fourier transform of signals of this particular nature. So let's say we have this xi of t. This has a Fourier transform of xi of j omega. Then we need to figure out, so we need to answer this question, what is the continuous time Fourier transform of xi of t minus t naught conjugate. Okay. Yeah. So for that, step 1, let us find out the Fourier transform of xi of t minus t naught. So this is the delayed version of my signal xi of t. So for this, we will use the time shift property. So what it says, if x of t is delayed by minus t naught, then in frequency domain, its Fourier transform gets scaled by this complex exponential. Okay. So therefore, this will have Fourier transform as xi of j omega. This will remain as it is, but it will get multiplied by e power minus j omega t naught. And now what we need to do is we need to xi conjugate of t minus t naught. So this will be what we need to do is, so for that let us define some notations again. Let's say this is some xi tilde of t, and this thing here is some xi tilde of j omega. So using the convolution property, the conjugate property, what we get is xi tilde of minus j omega conjugate. Okay. So now we need to replace, so in this xi of omega, j omega, we need to replace all of these omegas by a minus omega, and we need to take the conjugate. Okay. So this thing here is basically, first let us do this xi of minus j omega thing. So xi tilde of minus j omega. So that will be xi of minus j omega into e power minus j of minus omega t naught whole conjugate. So this comes out to be equal to xi conjugate of minus j omega into e power j minus omega t naught. So this comes out to be equal to xi conjugate of minus j omega into e power minus j omega t naught. So what does this mean? We had the signals of these forms. So from this particular derivation, what we know now is x1 conjugate of t minus t naught has a Fourier transform of x1 conjugate of minus j omega into e power minus j omega t naught. And similarly, x2 conjugate of t minus t naught has a Fourier transform of x2 conjugate of minus j omega e power minus j omega t naught. So therefore, x3 of t, which is equal to x1 conjugate of t minus t naught plus x2 conjugate of t minus t naught. This will have x3 of j omega as Fourier transform of this plus Fourier transform of this using linearity property. So what is Fourier transform of this particular thing? It is given by this thing here. So this comes out to be equal to x1 conjugate of minus j omega into e power minus j omega t naught plus x2 conjugate of minus j omega e power minus j omega t naught. And this is coming from, again, so this is coming from the linearity property. So let us clean it up a little bit. So this is equal to x1 conjugate of minus j omega plus x2 conjugate of minus j omega into e power minus j omega t naught. Now this is the value of x3 of j omega. We wanted to find out v of j omega, which is product of x1 of j omega, x2 of j omega, and x3 of j omega. So now let us substitute everything in one place. So therefore, v of j omega comes out to be equal to x1 of j omega, x2 of j omega, x3 of j omega, which is equal to x1 of j omega, x2 of j omega, multiplied by x3 of j omega, which is given by the equation here. So this is x1 conjugate of minus j omega plus x2 conjugate of minus j omega multiplied by e power minus j omega t. So this is the final answer. Any questions? Okay, if there are no questions, then let me move on to the next question. Okay. So this question is, we are given x1 of t equal to a1 cos omega t plus phi 1, x2 of t is a2 cos omega t plus phi 2, and x3 of t is a3 cos omega t plus phi 3. So these are the three sinusoids which are given to us. And what is asked, so what is the difference between these three sinusoids is they are having different amplitudes and different phases. However, these three sinusoids are of same frequency. So now it's said that each of this xi of t is sampled to obtain xi of n. And now x of n is equal to x1 of n, x2 of n, and x3 of n. And this almost perfectly reconstructed to obtain x of t equal to x1 of t, x2 of t, and x3 of t. It is found that xt is a sinusoidal signal and can be expressed in this particular form. That is, x of t is equal to a cos omega t plus phi. What are the values of a and phi? So basically, this line particularly given here is just to confuse you. What is asked is, we are given these three signals x1 of t, x2 of 3, and x3 of t. And we have this x of t as x1 of t plus x2 of t plus x3 of t. And this takes a form of a cos omega t plus phi. And here these x's that we are having, these x1, x2, and x3s, these are sinusoids of same frequency omega, but different phase and amplitude. And what is asked to us is, what is the value of a and phi? Okay, for that, let us start from the basics. So we have x of t equal to x1 of t plus x2 of t plus x3 of t. Now here this x1 of t is a1 cos omega t plus phi, plus we have a2 cos omega t plus phi 2. Sorry, this is phi 1. And we have plus a3 cos omega t plus phi 3. Okay, so now this comes out as a1, and now we can use cos a plus b formula, that is cos a cos b. So what we are using is cos of a plus b as cos a cos b minus cos sin a sin b. Okay, so using that, this first term comes out to be equal to cos of omega t cos of phi 1 minus sin of omega t sin of phi 1. Similarly, the second term becomes plus a2 cos of omega t cos of phi 2 minus sin of omega t sin of phi 2 plus a3 into cos of omega t into cos of phi 3 minus sin of omega t into sin of phi 3. So now if you observe here, this cos of omega t is common in these three terms. Similarly, the sin of omega t is common in these three terms. So now what we will do, we'll take the terms corresponding to cos of omega t common and that corresponding to sin of omega t as common. Okay, so now what we will get is cos of omega t, and the common terms are a1 cos phi 1 plus a2. So this is a1 cos phi 1 plus a2 cos phi 2 plus a3 cos phi 3. So a2 cos phi 2 plus a3 cos phi 3 minus, so we'll take up this minus sin of omega t common, minus sin of omega t divided by a1 sin phi 1 plus a2 sin phi 2 plus a3 sin phi 3. Okay. So we know that this entire thing is equal to a cos omega t plus phi. It is given to us. This is given to us here. Takes this particular form. So now let us simplify this. So this is equal to cos of omega t multiplied by a cos phi minus sin of omega t multiplied by a sin phi. So these two equations are same. So this equation and this equation are same. So now let us do the coefficient matching. So here the coefficient of cos of omega t should be equal to the coefficient of cos of omega t here. And similarly, the coefficient of sin of omega t in this above equation should be equal to the coefficient of sin of omega t in this particular equation. Okay. So now what we get is this a cos phi comes out to be equal to a1 cos phi 1 plus a2 cos phi 2 plus a3 cos phi 3. So we have A cos phi is equal to A1 cos phi 1 plus A2 cos phi 2 plus A3 cos phi 3. Now to make it in a write it in a concise way, we can write it as summation I equal to 1 to 3 AI cos of phi I. And similarly, we have this A sin phi is equal to A1 sin phi 1 plus A2 sin phi 2 plus A3 sin phi 3. So therefore, this A sin phi comes out to be equal to A1 sin phi 1 plus A2 sin phi 2 plus A3 sin phi 3. Again, we can write it as summation I equal to 1 to 3 AI sin phi I. Now we need to figure out what the value of A and phi is. So we can obtain this phi as sine inverse of summation I equal to 1 to 3 AI sin phi I divided by A, or this we can also write as cos inverse of summation. So let me just write it down. This is also equal to cos inverse of summation I equal to 1 to 3 AI cos phi I divided by A. And if I take the ratio of sine A sin phi upon the A cos phi, I'll get tan phi. So therefore, this tan of phi comes out to be equal to summation I equal to 1 to 3 AI sin phi I divided by summation I equal to 1 to 3 AI cos phi I. So therefore, this phi comes out to be equal to tan inverse of summation I equal to 1 to 3 AI sin phi I divided by summation I equal to 1 to 3 AI cos phi I. Okay, so this is the value, this is how we'll obtain the value of phi. However, we need to figure out how we will find the value of this A. So for that, what we will do is we'll add square of this and square of this. So what we will get is, so for A, we will do A cos phi square plus A sin phi square, which is equal to summation I equal to 1 to 3 AI cos phi I whole square plus summation I equal to 1 to 3 AI sin phi I whole square. So therefore, what we get is we get A square cos square phi plus sin square phi plus, sorry, not plus, equal to summation I equal to 1 to 3 AI cos phi I square plus summation I equal to 1 to 3 AI sin phi I whole square. Now this thing here is equal to 1. So A square comes out to be equal to the this particular term here. So therefore, A is equal to under root of summation I equal to 1 to 3 AI cos phi I square plus summation I equal to 1 to 3 AI sin phi I whole square. Yeah. So this is the value of A. And these three equations, one is this, and these give us the value of phi. So now we know the value of phi and a. So from that, this x of t can take this particular form, that is a cos omega t plus phi. Any questions? Okay, if there are no questions, then let me move on to the next question. Okay, so it is given that a signal having zero spectral content for frequency greater than f max. So it means that there is a signal, let's say some x of t, and we are trying to figure out its spectral content. That is, we are trying to plot its Fourier transform. So what we observe is, for my students, hero, so it has something like this, some Fourier transform like this, something like this. This is not the exact. So it's non-zero only in this region. It is zero after f max. So its frequency content is present only till this particular frequency, that is f max. So therefore, the maximum frequency in the signal is f max. Now it says, what is said is it is sampled. So this particular signal is sampled and quantized to get a 4-bit per sample at each step. So sampling we understand. That is, we are discretizing it at every time instant. What do we mean by quantization? So now what happens is, when we are sampling it along the time axis, we are getting discrete time samples, but the amplitude is again a continuous valued thing. Now, if we want to discretize that also, that process is known as quantization. And if we have to represent each of this quantization value or the quantized value, we use some number of bits. So what is said here is, for one sample that we get at one particular time instant, we require 4 bits to represent it. So what it means is, we sampled a signal to get x of n samples, and each of this x of n is quantized or is represented using 4 bits. Okay. What is the upper limit on f max? So what it asks is, what is the upper limit on f max such that the signal can be fed into a channel transmitting at a rate of 16 kilobits per second. So now what we need to do is, we need to send this from one device to another. I need to send that particular data, whatever I have, from one place to another, and the rate at which I am transmitting that thing is 16 kilobytes per second. So what we are doing is, we are transmitting, or we are sending 16 kilobytes of data in 1 second. So this is known as the data rate. And let's say this is given by this RD, and this RD is 16 kilobytes per second. which we can also write as 16 into bytes is 1 byte has 8 bits, and kilo is generally 1024. But for now, let us take up 10 raised to 3 bits per second. We want to transmit it using these many bits per second, which means that we need at least these many bits available. Okay. 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 So what we are having is this continuous time signal. So we had this continuous time signal and we sampled it using sampling frequency as Fs. Let's say as Fs. So this means that in 1 second, we get Fs samples. And one sample is represented using 4 bits. Therefore, in 1 second, we get 4 into Fs bits. Okay. So now, if we want to transmit this 4 into Fs bits per second, so what we had was this data rate, which was 16 into 8 into 10 raised to 3 bits per second. We can write it as the number. So in 1 second, we are having this 4s bits. So this thing should be equal to this 4s. Okay, so therefore my Fs should be equal to 16 into 8 into 10 raised to 3 upon 4. So this comes out to be equal to 32 kilohertz. Now we have a relation between this maximum frequency and the sampling frequency. So we have the sampling frequency to be greater than 2 times F max, or so therefore this F max should be less than this Fs by 2. So this is the upper limit of the maximum frequency that we need to figure out. So therefore this comes out to be equal to 32 kilohertz divided by 2, which is equal to 16 kilohertz. Is it clear? Any questions in this part? So the 16 kilohertz is the upper limit on the maximum frequency for a signal which we can transmit using a data rate of 16 kilobytes per second. Is it clear? Any questions in this part? Okay, if there are no questions, then let me move on to the next question then. Okay, so this question has 2 parts. This is a simple question. This doesn't involve any sort of calculations. This we have discussed, but still, let's do it one more time. So the first question says that aliasing in signal processing is caused under which conditions? So when does this aliasing in this sampling come up? Under which conditions?
When it is not followed by Nyquist rate.
Very correct. So this aliasing will come up will happen if yes Akash, when Fs is less than 2 2 times FM. That is, we are sampling it at a rate which is less than the prescribed rate by the Nyquist sampling theorem. Okay. Another question that this has is, which wave has infinite number of continuous derivatives or is known to have an analytic nature? So there are various functions which show this analytic nature. Two of them I will list here. One we have seen in the beginning of this lecture, that is the sinusoids. And another one is the exponentials. So we know that this ddx of e power x is equal to e power x, and same is with its integration. So we know that we have any order of, or let's say for that matter, nth order derivative is e power x. So these two are well-known analytic nature functions. There are many more, but for the sake of mentioning, I'm listing two of them here. Okay, simple questions. If you have any questions regarding them, just let me know. Otherwise, I'll move on to the next part. Okay, so what does this question 8 says? Which of the following continuous time systems are qualified enough to behave as an ideal low pass filter with a cutoff frequency equal to omega c? So we want an ideal low pass filter. So how does this ideal low pass filter look? So what does this low pass filter mean? It means that it passes all the lower frequencies and attenuates all the higher frequencies. So ideally what happens is, let's say this is 0, this is omega c, and this is minus omega c, this is omega c, this is omega axis, so capital omega. So what we want is this low pass filter should pass all the frequencies in this particular frequency region without any sort of attenuation or adding of phase, and it should not pass anything after omega c. So this is basically my h of j omega that I want. So this is the ideal low pass filter frequency domain representation. So it is passing all the frequencies between minus omega c and omega c, and no frequencies after omega c and before minus omega c. So for an ideal low pass filter, h of j omega, that is its Fourier transform, is given by 1 if this omega, capital omega, lies between these two, omega c and minus omega c, until 0 otherwise. Okay, so now this will have an inverse Fourier transform of, let's say, h of t. And suppose I want to pass a signal x of t in this system of h of t, which is a low pass filter. I'll get an output y of t, which will be equal to x of t convolved with h of t. Now, if you observe the options given to us, those are in the convolution form. So this x of t is getting convolved with some functions. So all of these functions which are listed here are basically the impulse responses, that is this h of t. So now we need to figure out how this h of t look like, and for that we will need to find the inverse Fourier transform of this. Okay, so therefore we need to find this h of t using this h of omega, which is 1 over 2 pi integral minus infinity to infinity h of j omega into e power j omega t d omega. So this is equal to 1 over 2 pi integral minus infinity to infinity. Now this h of j omega is basically non-zero only from minus omega c to omega c. Otherwise it is 0. And in this particular region, it is 1 into e power j omega t omega. So this comes out to be equal to 1 over 2 pi e power j omega. Integration is e power j omega t upon jt from minus omega c to omega c. So this comes out to be equal to e power j omega c t minus e power minus j omega c t divided by 2 pi j t. So this is h of t. So this is the impulse response that we are interested in. So if we look at this option 2, that is e power j omega c t minus e power minus j omega ct divided by 2 pi j_t. So this is exactly the expression that we were in, where that we got. So this is the answer to our question. Is it clear? Any questions?
Ma'am, is it possible
Yes.
that h of omega is always a 1, or it may be anything, any other magnitude?
Okay, so basically what our goal is that we don't want to amplify or we don't want to attenuate that particular signal in the allowable frequency range. So that's why we want the amplitude to be 1. Now, suppose you want to amplify, let's say you want to double the amplitude in that particular frequency range, then you can set it to be 2 in that region. However, when I just want to design a filter that passes those frequencies, it neither changes its amplitude nor its phase. In that situation, I need to keep the amplitude as 1. Does that answer your question?
Yes, ma'am. Or we can say that we are amplified by the variable a or gain parameter a. So that will
Yes.
be scaling by. Okay.
Yes. 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 Any other questions? Okay, if there are no questions, then let me move on to the next question. Okay, just don't get intimidated by this big question. After you read this entire thing, it will be a very small thing that is being asked in this question. So again, this is an example of how these people can put questions in your assignments or in your exams that will just make you look at this question and get afraid, and it will be a very simple thing that is being asked. So let us see what they are saying here, what story they are trying to say here. So it says that suppose our task is to sample a pure sinusoid signal, which is x of t equal to a sine 2 pi f naught t. So this is the sinusoid that they want to sample at a sampling frequency of fs and the sampling duration of ts, which is 1 by fs. We knew that. So it says that we knew that from the same sampled signal, multiple sinusoidal reconstructions are possible. For example, x1 of t equal to a sine 2 pi f naught plus minus k fst on sampling gives us discrete time signal x of n, which is a sine 2 pi f naught plus minus k fs nt, a sine 2 pi f naught nts plus minus 2 pi kn, and a sine 2 pi f naught ts. This is the same as what we would get by sampling x of t. So what it says is we have an x signal x of t, and if we sample it at a sampling frequency fs, so we will get multiple sinusoidal reconstructions or multiple sampled versions also of that signal, which will take up this particular form. Now, suppose we look at another sinusoid, which is given by this equation here, which is x1 of t equal to a sine 2 pi f naught, and you are just adding plus minus kfs. So now if we sample this particular signal, again, we will get the same set of equations or the same set of sinusoids or signals, discrete time representation. So now there are infinitely many such sinusoids possible that can be sampled to get the same discrete time signal. So if I go on changing my case, I will get different sinusoids, and again I will get the same discrete time representation for those all sinusoid. Suppose we try to reconstruct the original signal by taking the sum of all such possible sinusoids and passing it through a suitable ideal low pass signal to get a single sinusoid for which of these sampling frequencies we would correctly get back the original signal x of t. Now suppose the sampling is done at the time instance t equal to nts. So what they are saying is we want to sample the sinusoid x of t equal to a sine 2 pi f naught t, and we want to reconstruct it back properly. There are other replicas and mirror images that come up, but we don't want them to be present in our reconstruction. So we want a suitable sampling frequency in order to sample this particular signal x of t. So what are the possible values of sampling frequencies that we can take up? So here they have given 4 options. One is Fs, which is equal to 0.5 F naught. Another is Fs equal to F naught, Fs equal to 2 F naught, and Fs equal to 2.5 F naught. So now we have seen that if I want to sample x of t equal to a cos 2 pi F naught t plus phi. So this is the frequency, that is f naught, that is present in this particular signal x of t. So we want this sampling frequency fs to be greater than 2 times f naught. Right. So any frequency, any sampling frequency which is greater than this 2 times f naught will give us the proper reconstruction. So now which are the possible values that will give us given an option that satisfy this particular condition? So one is this 0.5 f naught, another is f naught, another is 2 f naught, and the last one is 2.5 f naught. So the only value of fs which is greater than this 2 f naught is this last option, that is this one, that is fs equal to 2.5 f naught. Is it clear? So this answer comes from this Nyquist sampling rate. Is it clear? Any questions? Okay, if there are no questions, then let me move on to the next question. So this is the last question that I'll be taking up today. Okay, so this question says, one of the most common ways of obtaining the sampled version of an analog signal is to perform uniform sampling of the signal by multiplying it with a train of impulses, each shifted from the previous by Ts sampling duration. So here whatever they have given, that is P of T, which is summation of this unit impulses shifted by by the integer multiple of Ts. So this is known as the train of impulse. And why is it called the train of impulse? So this is just because how that signal looks. So at 0 we have delta t, then at ts we will again have an impulse, then we'll have an impulse at 2ts and so on. Similarly, we'll have it at minus ts, minus 2ts and so on. So it looks like a train of impulses. That's why it's called a train of impulses. Just a visual understanding of that. Okay. So now this is called a train. This is called impulse train sampling or uniform sampling. We perform the same for two cases in this problem. So we'll see those two cases. So the first thing that is given to us is let x of t be the given analog signal with this particular Fourier transform. Okay, so this is the particular Fourier transform that is given to us. So how does that Fourier transform look? So what is given to us is x of j omega. This is equal to omega by omega m plus 1 if minus omega m less than or equal to omega less than or equal to 0, and this is equal to minus omega by omega m plus 1 if 0 less than omega less than or equal to omega m. So how does this look? So let us try to plot it. We have this omega, then we have this vertical axis as x of j omega. Then let's say we have this as minus omega m, and we have this as omega m. So if I substitute omega equal to minus omega here, so what we get is 0. So it is 0 at minus omega, and as if we substitute omega equal to 0, it comes out to be equal to 1. It's a linear function, linear function which is having a positive slope. Now similarly, for omega equal to omega m, if we substitute it in this equation, it again comes out to be equal to 0. And this is a decreasing linear function from omega equal to 0 to omega m. So this is how does this x of j omega look like. So this is the visual representation of my x of j omega. Now what is asked to us is this p of t is also given, and xp of t is x of t multiplied by this p of t. That is, we are multiplying this particular signal x of t by this train of impulse. So what will happen is this train of impulse will pick up the value at that particular sampling duration and make all others zeros. Okay, so now we perform this impulse train sampling for case 1 STS less than pi by omega m, and case 2 STS greater than pi by omega m. So what is given to us is let area under xp of j omega, where this xp of j omega is Fourier transform of xp of t, and the areas are given for different regions. That is one from minus omega m and omega m as a, omega m and 2 pi by ts minus omega m as a1, and 0 to 2 pi by ts as a2. And we need to relate these areas a1 and a2 for both the cases. That is case 1 and case 2. Okay, I think I made some mistake here. This should be 0. Yeah, okay. Okay, this is what we are having here. No, this is okay. Yeah, from minus omega m to omega m. Yeah. Okay, so we need to find the relations between this A1 and A2. Now, in order to find the relations between these three areas, we first need to figure out what this xp of j of omega is. So now what is given to us is this xp of t is x of t into p of t. Okay, so now if I take Fourier transform of this is xp of j omega, which is equal to, there is multiplication in time domain, so there will be a convolution in frequency domain, but it will be scaled. So we will have 2 pi x of j omega convolved with P of j omega. Now x of j omega we know. What we don't know is P of j omega. Okay. So how does this P of t look? This P of t is summation n equal to minus infinity to infinity delta t minus nts. Okay, so this we have. And now what happens is this thing is train of impulse. And if you observe here, we have drawn this diagram. This is our P of t. So this is a periodic signal with period ts. Okay, so this particular signal, this is periodic with period ts. Okay, so for a periodic signal P of t, the Fourier transform, that is P of j omega, is given by 2 pi summation k running from minus infinity to infinity ak del of omega minus omega s, where this omega s is basically 2 pi by ts, which is its fundamental frequency. And this ak's are Fourier series coefficients. Okay. So therefore, first we need to figure out what these AKs are. So this AK is given by one by Ts over a period of Ts. So let's take it from Ts by 2 to Ts by 2. P of t into e power minus j k omega s t dt. Okay, now in this region of minus Ts by 2 to Ts by 2, that is in this region, my P of t, sorry, in this region, my P of t is equal to delta t. So therefore, what we get is, so this thing is equal to 1 over Ts integral minus Ts by 2 to Ts by 2 delta t into e power minus j k omega s t dt. This is a unit impulse. So we know the shifting property of this unit impulse. So this will make, so this particular thing that gets multiplied will take up the value of unit impulse where it is present. So this unit impulse is present at t equal to 0. So we'll substitute t equal to 0 in this particular term and take it outside. So this is equal to 1 over Ts integral minus Ts by 2 to Ts by 2 delta t into e power minus j k omega s into 0 dt, which is equal to 1 over Ts integral minus Ts by 2 to Ts by 2 delta t, because this thing comes out to be equal to 1, and we are integrating a region in which this impulse is present. So again, this thing comes out to be equal to 1. So therefore, my AKs comes out to be equal to 1 over Ts. Okay, so therefore, AK comes out to be equal to 1 over Ts. So now we can substitute it back to P of j omega, which was equal to 2 pi summation k equal to minus infinity to infinity AKs, which comes out to be equal to 1 over Ts into delta omega minus k times omega s. So this comes out to be equal to 2 pi by Ts summation k equal to minus infinity to infinity delta omega minus k times omega s. Now let us substitute this back to the expression of our xp of j of omega. So therefore, that was the end goal that we wanted to figure out. So therefore, xp of j of omega is equal to xp of j, x of j omega convolved with p of j omega, that is 2 pi by ts, summation k equal to minus infinity to infinity delta omega minus k omega s. Now, since this is this convolution is distributive over additions, so we have 2 pi by ts summation k running from, and we had a scale equal to pi, so this gets cancelled. Minus infinity to infinity x of j omega convolved with delta omega minus k omega s. So now this is equal to 1 upon ts summation k running from minus infinity to infinity x of j omega minus k omega s. Okay, so what is happening here is, if we look at xp of j omega, this is equal to 1 over ts summation k running from minus infinity to infinity x of j omega minus k times omega s. Okay, so this is what we are having here. Okay, so what does this mean? This means that we are shifting x of j omega by integer multiples of omega s and adding them. Okay, so what is happening is, we have this is, let's say, 0. This is omega s. This was omega m. This was minus omega m. Let's say this is minus omega s. So what is happening now is, we are having this thing here, that is 1 over ts. It was 1 initially, but now we are having 1 over ts. And similarly, we will have the replicas present at omega s and at minus omega s, and at every integer multiple of omega s. So this is how our xp of j omega look. Now let us look at what is being asked. So this is the case when my omega s minus omega m is greater than omega m. It might happen that it overlaps. So that is another thing. So for now, let us look at the three areas that were asked to us. I'll just copy this and move the page. Okay. Okay. Yeah. So this is what we are having. So we are having two cases. For the case one, so let us start with the case one. So case one is the case when we have Ts less than pi by omega m, which means that we have omega m less than or equal to pi by Ts. So if I multiply both sides by 2, so we have 2 omega m less than, this is basically omega s. So we have omega s greater than omega m, that is, we have omega m less than omega s minus omega m. So this is exactly the same situation that we have drawn here. So let me take it here. So now what is given to us is, the area between this omega m minus omega m and omega m is A. The area between omega m and this region is A1. And the area between this 0 2 omega s. So this thing here is basically omega s. Omega s is A2. Okay, so now since it is symmetric, this particular region will have an area of A by 2. Similarly, this particular region will have an area of A by 2. Okay. Okay, fine. So now since we have this thing, what we can do, what we observe is this A2 comes out to be equal to this region, that is A by 2, plus this region, that is again A by 2, plus this region A1. But this A1 is equal to 0. So this comes out to be equal to A by 2 plus A by 2, which is equal to A. So this particular area, that is A2, comes out to be equal to A. Okay, so this was for case 1. The case 2 is opposite case. So case 2 is the one where we have Ts, which is greater than pi by omega m, which means that this omega s is less than 2 times omega m. That is, this omega s minus omega m is less than this omega m. So what we have is that we'll have overlaps. So now we will have overlaps. Take it like this, something like this. So this will go here, and this omega s will be somewhere here. And similarly, in this side also, we will have overlap. So now again, what we have is this particular region, same thing. So same thing, this was A. This entire region is A, but this half thing is A by 2. Similarly, this half thing will again be A by 2. And now we need to, this region, this particular region is having the area of A2. Okay, and this region has an area of A1. Okay, so now we need to figure out the area under this curve. So basically, when we are showing this overlap here now, this particular thing gets added. So this looks like this. This basically looks like this, and so on. So now again, we need to figure out what this A2 is. Okay, so this A2, we can write it as integral from 0 to omega s xp of omega d omega. Okay, so now this thing, we can write it as 0 to, let's say, omega s minus omega m. In this region, this will be equal to xp of omega t omega, or in this particular region, this will be equal to 1 over ts x of omega t omega plus integral omega s minus omega m to omega s. This comes out to be equal to 1 over ts again, but x of omega minus omega s. So let me put a j here just for notational consistency. Okay, so this is what we are having now. Now again, okay, so we have this now. Now we can write this actually with a little bit different notations, or Wait a minute. Wait a minute. Yeah, so we can write it from omega s minus m to omega m. So here it is overlap of two things. So that is 1 over Ts x of j omega plus x of j omega minus omega s, and plus from omega m to omega s, it is again 1 over Ts x of j of omega minus omega s d omega. So now this thing here, we can split this summation here, and we can combine this part, and again we can combine this part together. So what we get now is this is equal to integral 0 to omega m 1 over Ts x of j omega d omega plus integral omega s minus omega m to omega s 1 over Ts x of j omega minus omega s. Now, if you observe carefully, this is this region. This again has an area of a by 2. So the first thing here will have area of a by 2, and second region from omega s minus omega m to omega s is this region. This again has an area of a by 2. So again, for this case also, the area comes as A. Any questions? This was the last question that I had planned to cover today. If you have any questions, then let me know. If you don't have any questions, thank you for attending today's session. See you all on next Friday.
Yeah, just one thing.
Yeah.
Will you be sharing the slides of this tutorial?
Yes, it will be shared.
Okay, okay. And just one more thing. Thanks for your tutorial session. There are some topics related to that continuous time Fourier transform and the properties. The convolution properties and all. These were not covered in the week one means the slides means of the lectures.
Yeah.
So will this be in this week 2 lecture? Because these are not there in the
Actually,
first week lectures.
yeah, actually these continuous time Fourier transform, and these are basically prerequisites, and they come from signals and systems course. So this is the course that comes
Okay.
after signals and systems.
Okay.
So in case you have any specific queries in that, this just you can post it in the Q&A portal. I will take them up in the next session if you want.
Okay.
Yeah.
Fine. Okay. Thank you. Thank you.
Yeah. If you don't have any further questions, you're free to leave the meeting. Thanks again for attending.